Okay, so hi to everyone. I'm sorry I couldn't be there in person. So this talk is going to be about faster no-regret learning dynamics for extensive form correlated equilibria. And it is a joint work with Gabriele, Farina, Kroer, Andrea, Celli, and Tuomas, Sandholm. So naturally, understanding the behavior of no-regret learning in games is central for many applications ranging from economics to machine learning and AI. For this talk, we're going to follow a recent line of work that focuses on establishing improved regret guarantees when all players in a game employ specific learning dynamics. And in particular, one common goal is to outperform the guarantees that are possible in the adversarial regime. That is, if the player is facing a sequence of utilities that are chosen in adversarial function. So let me first highlight some of the key contributions in this line of work. First of all, it was shown that it's possible to obtain exponentially improved guarantees when both players in a zero-sum game employ specific learning dynamics. And that result was subsequently simplified by introducing the very natural an important framework of optimistic online learning, which we're going to review later in this talk. Nevertheless, those works only considered zero-sum games, and it was only Ioannis et al. Who obtained the first results for general games. Although the guarantee that they obtained did not quite match the ones we saw for zero-sum games. And that gap was breached very recently, in fact, last year. So the main takeaway of this, all of those results, is that it's possible to converge with a rate of 1 over t to the set of coarse correlated equilibria in general normal form games. So this talk is going to focus on extending those type of guarantees along two main axes. The first one is going beyond coarse correlated equilibria. So indeed, coarse correlated equilibria is understood to be a rather weak equilibrium concept. And in certain scenarios, it can really prescribe irrational behavior. On the other hand, correlated equilibria is a much more compelling solution concept. So the natural question here is whether it's possible to obtain similar accelerated results for no-swap regret learning dynamics. And here recall that swap regret is associated with correlated equilibria, while external is associated with coarse correlated equilibria. And indeed, Chen and Peng first addressed this question quite recently, where they managed to extend the results of Ioannis et al. From external to swap regret. And we are going to, in fact, revisit some of their key insights later in this talk. Nevertheless, all of those works are considering normal form games, which brings us to the second main focus of this talk, which is going to be about going beyond normal form games, in particular going to extensive form games. So extensive form games generalize normal form games by modeling both sequential and simultaneous moves, as well as imperfect information. And as such, they are more realistic models of many practical applications. Nevertheless, because of the sequential aspect of the play, correlation extensive form games is much more intricate, and it is much less understood compared to normal form games. I should note here that some of the previous results we saw for external regret can be extended for extensive form games. But going beyond coarse correlated equilibria, correlation is much more intricate. And indeed, there have been many notions of correlations that have been proposed throughout the years that mainly differ on the way the players receive recommendations from the so-called mediator. In fact, there is a whole hierarchy of solution concepts. But for this talk, we're going to focus on extensive form correlated equilibria, or EFC, which is in fact the stronger notion of correlation, which is known to be computationally tractable in extensive form games. Now, because of the complexity of EFC, it was only very recent work that showed that there exist uncoupled no-regret learning dynamics that converge to the set of EFC. And it was only last year that the same authors obtained explicit rates of convergence of the form 1 over square root of t, which is the guarantees one might expect from traditional techniques in the no-regret learning framework. So this brings us to the main contribution that I'm going to describe in this talk, which is the first accelerated dynamics for EFC that converges with a much faster rate of 2 to the minus 3/4. And this will generalize a result of Sirkanis et al. As well as Celli and Peng. So before I sketch some of the main components of our construction, let us first revisit the basic principles of acceleration for external regret. So the first one is what it is referred to as optimism. So if we assume that there is some form of structure and the sequence of observed utilities, we might as well use some form of a prediction mechanism to leverage that structure. And indeed, optimistic follow the regularized later, or FTRL, is a very minor modification of FTRL, with the slight difference that the utility the learner observed in the last round is going to be counted twice. So there is this form of a recency bias in that we're giving more weights to more recent utilities. And this type of strategy makes sense as long as there is stability in the sequence of utilities. That is, as long as the utilities the learner observes change slowly over time. And this, in fact, is going to be the case when all players, even in a general game, employ regularized learning algorithms. Nevertheless, the main focus of this talk is going beyond external regret. And to do so, we're going to use the notion of high regret, which is a very general performance measure in online learning, parameterized by a set of deviations phi, so that the performance of the learning agent is now compared to the best performance the learner could have obtained by optimally deviating based on the set of deviations phi. So here, note that phi regret captures external simply in the case where phi only includes constant transformations. But the whole point here is that as phi gets richer and richer, we recover stronger and stronger notions of hindsight rationality. And from an algorithmic standpoint, it turns out that there's a very general reduction that essentially reduces phi regret minimization to external regret minimization. And that reduction requires two basic ingredients. The first one is an external regret minimizer, but with the twist that now we are operating over the set of deviations phi. And to give you an idea of what this means, say, for example, in normal form games and for swap regret, it means that now we have to operate over stochastic matrices instead of probability distributions. So now the set, let's say the standard set is a much more intricate combinatorial set. And the second ingredient is a fixed point oracle. So it better be the case that for any possible deviation, there is a fixed point. And furthermore, that fixed point can be computed efficiently. For example, again, for normal form games, this fixed point operation simply corresponds to the stationary distribution of a Markov chain. Okay, so since there is this general reduction, the main question is whether it's possible to automatically translate the accelerated results we saw earlier from external to phi regret. However, the answer is very delicate. And in fact, even stability, this very basic component of acceleration that we saw earlier, could completely fail for phi regret learners. So this was observed by Celli and Peng, who made the first progress on this problem, who basically noticed that even though the transition probabilities of a Markov chain could change very slowly over time, there is still no way of guaranteeing that the stationary distribution will also change slowly over time. Indeed, in this figure that I took from the paper, there is a counterexample that the stationary distribution, which corresponds to this fixed point operation we saw earlier, can really cause a large instability in the sequence of strategies. Nevertheless, it turns out there is a very elegant solution to bypass this obstacle, which revolves around using a refined notion of stability that we're going to refer to as multiplicative stability, which simply means that every two successive strategies have to be close in terms of multiplicative deviations. So here notice that generic FTRL type of dynamics do not satisfy this refined notion of stability. But the whole point is that if you use multiplicative weights or, say, optimistic variants thereof, you can actually ensure this type of stability. And so the key insight here is that if the transition probabilities of a Markov chain are multiplicatively stable, then you can show that the sequence of stationary distributions will also be stable. And this can be, in fact, shown using the Markov chain tree theorem. And using this observation, Chen and Peng were able to extend the results of Ioannis et al. From external to swap regret. Okay, so let me now briefly explain some of the challenges we face for EFC. Okay, so in terms of stability, it turns out that the fixed points associated with EFC can be computed in a dynamic programming type of approach by essentially computing stationary distributions along paths of the tree. Now, a main challenge that arises is that if one uses prior techniques, the stability degradation will be in fact exponential in the size of the gain. In particular, it would have this dependence on the product of the number of actions along paths of the tree, which could be exponential. So instead, we managed to show a refined stability bound using the following refined analysis of stability. And here, to give you an idea, the observation is that every time you have to compute a stationary distribution, the underlying Markov chain can be decomposed into two components, so that one of the two components is a rank 1 stochastic matrix. And the key observation is that the exponential degradation that we encountered earlier derives directly from this rank 1 component. So for this reason, we refined the guarantee of the Markov chain tree theorem for that particular class of Markov chains, establishing that the stationary distribution only depends in an affine way from the rank 1 component, so that all of the coefficients of this transformation are non-negative. And this is crucial because it allows to show that the multiplicative deviation of the stationary distribution degrades very gracefully in terms of the multiplicative deviation of the rank 1 component. And this allows to obtain polynomial dependencies in terms of the stability. Okay, so having established guarantees in terms of the stability, the next step is to construct a predictive regret minimizer that is operating over the set of all possible deviations. And to do so, we employ two approaches that are typically employed separately. So the first one is what is sometimes referred to as the regret decomposition. So we start from a structured combinatorial set, and we decompose this set into simpler sets, so that for any simpler set, we can perform efficiently optimistic online learning. And the second ingredient is to construct appropriate distance generating functions, again, to perform FTRL steps in certain combinatorial sets. Okay, so let me now illustrate some experimental results. So here we tested several learning dynamics in some benchmark extensive-form games. And all of those learning dynamics are designed specifically to converge to EFC. So all of them have an EFC gap. But as you can see, the rate of convergence could vary substantially. In particular, using optimistic variants can have substantial impact on the rate of convergence, outperforming methods which are state-of-the-art, for example, in zero-sum games. So, for example, in Serif, a game that was introduced specifically for its interesting correlated equilibria, we see that the difference is many orders of magnitude. And finally, let me describe some interesting future directions that relate to our results. The first question is whether it's possible to obtain near optimal 1/t rates for EFC. While there are some recent results for normal form games, the techniques that are used there are hard to extend for EFC because of the complexity of the set of deviations, as well as the complexity of the associated fixed points. Another interesting direction is to obtain better dependencies on the size of the game, that I have implicitly suppressed throughout this talk to simplify the exposition. And finally, everything we have discussed in this talk is about the full information setting. Now, it turns out that in the standard banded setting, it's not possible to get guarantees beyond square root of t. But it's still interesting to find partial information models that are well motivated and for which it's possible to obtain meaningful accelerated results. And with that, I conclude the presentation. I'll be happy to take any questions.
Yeah, thanks a lot, Ioannis, for the great talk. So we have about right now 2-3 minutes for questions. So if anyone has a question, either virtually or in person, please come up. And it'd be great if you just came up directly to the mic so that people online can hear you fine.
Hi. So I was wondering, empirically, do you guys observe the 1/t convergence, or is it this 1/3/4 t?
That's a very good question. So the answer depends on how you tune the learning rate. So in fact, so using the learning rate that is theoretically predicted by our theory, we do observe essentially t to the -3/4. But we believe that if you tune the learning rate to be, for example, a constant, it's possible to get 1/t. But the problem is that there is no theory. If you use a constant learning rate, in principle, you could even have linear regret. There is absolutely no guarantee that you can have even sublinear regret. So yeah, the answer to your question really depends on how you tune the learning rate. So using the best theoretically valid value for the learning rate, indeed gives rate which is roughly to the -3/4.
So do you think that in order to get this 1/t convergence, you need a new algorithm or a more refined analysis of the same algorithm?
I believe even the same algorithm has 1/t, but again, with a different, I think the main challenge is the analysis, really. I think the algorithm probably already gives 1/t for a certain value of learning rate, though. The learning rate is very important for the rate of convergence.
Cool, thanks.